So just to give a short review from the day yesterday. Yesterday I started at the beginning with some estimations or some background to the material science and due to the correct appearance. And at the ending, we did here our first fatigue assessment. So we used here, for example, this amount of numbers of cycles. So around 8.66 over 10 over 5 and 100 MPa with an R ratio. So the R ratio is the value between the lowest stress to the highest stress in our load system. And at the end, we could do with this information and a chosen notch detail of a notch class of 80, our okay. Oh, good morning. We could do the first fatigue assessment, and as you can see here, with the 100 MPa and the 8.55 10 over 5 cycles, we got a fatigue damage due to a linear damage accumulation of 0.84. So what I want to go today at first to focus on is the importance of the mean value assessment. So because this one is always, I was also looking yesterday onto this one, and as you can see here, the mean value is always related to the stress ratio regarding to the recommendations or to the guidelines usually you have in the fatigue assessment. And so if you go, for example, to this detail again, we see, okay, for a stress range value of 100 MPa and an R ratio of 0.5, we have a top peak stress of 200 MPa and the lower stress of 100 MPa and the mean value of 150. So if we now change here, for example, our value to 0.1, sorry, you see we have still the same stress ratio, but the same stress range, but regarding to the stress ratio, we have here a top value of sigma 111 and a lower value of 11.1 MPa. And this is also the stress ratio of 0.1 is usually the ratio the fatigue tests are done, because there you have a low amount of cycles, so it's not as cost extensive, and also you're not going through the 0.0 into the pressure, which is always a little bit not as good for the testing machines, but also for the steering in itself. So what is happening if we change now our stress ratio? There are, for example, in example in the literature which I found there is, for example, for this kind of notch specimen, so a specimen with a cruciform joint, and this cruciform joint has here some plate, some fillet inside, and it is valid from both sides. And we have also in all specimens there's regularly a root failure with the size of 2 millimeters. So, and now the material of these specimens is the S355, in former regulations ST52-3. And so it was tested with an R value of -1. This is the blue one. And an R value of 0. This is the red one. So as you can see here, due to the R value, you have a movement in this direction. So if the R is gonna be decreased, it goes upwards. If the R is gonna be increased, it is lowering. So, and usually in our fatigue design curves, we are calculating with an R of 0.5, which is at this value. And this is also the references we have, therefore, in our code. So this is what they are saying. And but it doesn't, if you go through the specimens, it does not always fit properly. So it can also be something a little bit lower and so on. So, and what has been done to find the resolution, how to estimate or how to get this value into your design. So there have been several approaches which at the end are combined in this diagram. So for example, which we have here our design curves, or the estimated curves with our point and notches. So these are our fatigue data. This is our regression curve. And therefore, at the same time, we can do it as we have here for a second R value of the same specimen, of the same welding. And at the end, you're just going to evaluate the values at a specific numbers of cycles, like n 10/4, 10/5, 10/6, 10/7. And you just define here the ratio between the lowest one at this point and the highest peak at the point. And this is at the end the value which you can see here. So you have at this point you have your R ratio, and at this side you have the increasing amount, which is the ratio between your reference system and some R value which you gonna have tested in the whole testing series. So, and due to this, you can find there, for example, to each numbers of cycles, some reference due to the R value. And this is, for example, shown in this diagram. And in this diagram, at the end, you can find there two different approaches. So at first, you can see also how the ratio is increasing by the lowering of the R value. And at the second stage, you can see here the first approach, which is depending on an estimation of 60% amount of pressure value. So this is what they say here, for example, that at the end, if you have, for example, some pressure, so some R value which is lower than 0 in your structure, and the specimen, for example, the welding is annealed, or it is a raw base material, then you can decrease your stress range by 60% of the lowest peak. And so you can recalculate your new stress range. So this is what is shown at this site. So the straight line. And the top line is a second approach, which is also which you can also find in some regulations. And this is just, as you can see here, it is just also the regression curve. And you say, okay, the lowest point of interest is always the -1. And at the end, you can define, due to your regression, a curve which fits to this equation. And so this equation says rho is minus r/3 plus 4/3. And so this is a second approach. And this is, as I said, in all regulation as you can find. And to see what are here the differences, we're going to go through one detail with the same notch detail, the same amount of cycles, the same amount of the R value. And at the end, we're going to see, okay, how these two approaches can be equal or similar at this stage. So again, we start here with our R value of of 0.1, and as we had already here, this is our stress range behavior in the time series. And now we want to go at first into our different approaches and recalculate our different factors and how they're influencing our system. So, sorry. So this is, as I said already, the 60% assumption, which is recommended in the Eurocode, but also as I know somewhere in the back mind, in the AASHTO. And here, for example, as I explained already, you have the lowering of the stress range by the 60% of the lowest peak, which is already in the pressure. So, for example, if at this time you have an R value which is higher than 0, you have no pressure inside your structure, so you have also no lowering. So, what is the second approach? This one looks like this. So the formula, the equation you had before, just a little bit reorganized. At the end, it looks like FR. So this is called the bonus factor, which we're going to apply on our damage curve, is 1.2 minus 0.4 times R. And as you can see here, the reduction already started by a point of 0.5. So compared to the first estimation, we already have here, for an R value of 0.1, some benefit in our design. And okay. So, and now, if we go again, what I already explained here, we have our, for the R value, for the 60%, we have no decreasing of our stress range, but at this point, we already get a bonus value of FR. And at the end, sorry, Somehow my computer is a little bit slow today. Okay, thanks a lot. So, and at the end, you get here, there should be also some drawing. Okay, so at the end, you have here the rule with the 60%. So as it's already said, due to the chosen R value of 0.1, you have no decreasing of your stress amount here at this point. So you have the same damage, linear damage factor or accumulation of 0.84. And on the other side, you have here at this side an increasing of your SN curve. So the value of your delta sigma C, which we have chosen before as 80, has now a new value of 80 times 1.16. And this is our value FR. And due to this, as you can see here, you move your SN curve upwards. Due to this, at the same stage, you can handle a higher amount of cycles. So instead of the 1.1 million times 24 over 24,000, around 1.6 million cycles. And at the end, you have a better estimation and a better accumulation at the end of 0.54. So you can have a benefit at this side on your fatigue assessment and on your calculations. So, of course, this is something which is which you have to do in the engineering office, and you have at the same time you have to be sure that you can take at this stage this R value of 0.1 or some different, and because as you can see here, also in the damage or also in the amount of cycles, there is a huge difference, which is just chosen or just implied in the system or in the damage accumulation due to a different assumption for the mean value. So, and this difference and this difference you can also see here, of course, in the chosen mean value assumption. So as you can see here, of course, this is always the ratio and the benefit according to a curve of R 0.5. So this distance also shows at this time the distance from here to here. So of course, if you're going into this direction, also in this side, we already have some benefits which just occur due to the different assumptions we have there. Which assumption at the end is the better one? There is always the discussion. And but as you can see here, for example, in the different codes in civil engineering in Europe, we apply, for example, this curve for aluminum structures and the lower curve for steel structures. If you go for IAW, which is a recommendation for steel structures from the International Institute of Welding in England, in the UK, they also take this curve for steel structures. So At this side, there is no real meaning, but for, I would say, for pre-design and preliminary design in civil engineering, this could be also a very good one, because at the end, you want to have a durable design and a durable system. So, due to this, that yesterday there were less questions, are there some questions regarding to this point? Otherwise, I just continue. Okay, so the other point we already somehow looked on yesterday was at the finishing of the theory part. There I showed a small detail which looked like this. Yeah, there is a curve again. And at the same point, we had here a hole. So, and for example, in our design curves, this hole is not really specified, so we cannot say, okay, how do we gonna take it? How can we take this into our account in our estimation? But still, just to show what the influence of a notch means, I also have here some testing procedure or some testing results where we can see how at first how a notch, so how the increasement also influences your curves. And at the second stage, I want to go again in my today a little bit slow Excel sheet and go there and show you what or how you can take this into account into your estimations and how this gonna influences all your approaches or also the design. So at first, if you look here, this is, for example, the whole summary of some different concepts you have there. So this is the nominal approach. And these are some local approaches, which at the end ends up here with the fracture mechanics. And this is a point I hopefully gonna start in the second term of this day and just go and get a short overview there to see, okay, what are the benefits, but also the testing procedures you have to go and do there. So in your nominal stress evaluation, usually, for example, for this plate, you have here your normal forces and your bending forces. So at the end, this stresses results in a constant value and also in a linear value. But for example, if you have at the same time a hole inside, next to the hole, you have a stress increasement, and the stress increasement is always called or announced as the stress concentration. Factor KT. And therefore, in the literature, you can find, for example, different compendiums where you're going to find solutions, linear solutions for something like this, but also for other situations. And therefore, so at the end, you can easily calculate the KT. Otherwise, you have to go and do some numerical investigation and also get your value KT. So how does it look like? If we're going to test some different specimens. So of course, the specimens at the same time here look a little bit curious. but this point, we just wanted to look at these points here, where we always somehow changed our radius, the size into the specimen, and at the end could also change at this stage the stress concentration next to this point, and also change due to this the amount of cycles. So as you already can see here, we have an KT of 3.7, which is, I would say, also still common for structures we have in civil engineering. This I would shift and say, okay, this is usually some point where we usually not design, and we would say, okay, let's do some smooth curves and get some other solutions. So, but at the end, for example, for mechanical engineering, there you can also have some deeper notches, which at the end up by a value of 20 or 15. So how does it look like if you go for a small analysis? Of course, this net at this part is not perfect, but you already see, okay, for a KT of 7 with an Poisson ratio of 0.3. At this stage, you get a 10.5.28. If you now change and you take the, sorry, I have to add some information, and the S1, so the first stresses in your system, you have a value of 10.528 around. If you take the S epsilon to see, okay, how is our coordinate system orientated, so our orientation here goes in this direction, sorry. Goes in this direction, sigma 1. Sigma 1 is in this direction, so along the surface. Sigma 1 is orientated in our local coordinate system, which you can also see here. And due to this, of course, we have some change of our amount of stresses. So at the end, which will be also referenced to the KT, is at the end the sigma 1. And but also, of course, at this part, just to show the difference between the taking account the Poisson ratio of 0.3 or not, you can see here that you have at the same stage for the sigma 1 the 9.1 and at the other side the 8.5. So you have a small, due to the 3D system or 3D calculation at this time and taking into account the Poisson ratio, you have an increasement of 0.6, which of course you're gonna not have in this situation if you, for example, go there and would calculate for shell structures or something else. So there, this would be not as good fit to the situation. So, but how is it going to be in the testing results? So what I have here in this time is an aluminum alloy, AlMgSe1. So this is as we some no, Alg. 682 aluminum alloy, and this alloy is always tested with an R value of -1. And as you can see here, for example, our KT of 3.7, we reach, for example, for 10/7, a value which is around 80 MPa. If we now go for a KT of 2 × 2, we are somewhere here, which is around 35 MPa. So as you can see here, just due to the influence of the notches, we have at this side, which is still just in an elastic area, a decreasing of our stresses we can handle there for the same amount of numbers of cycles. At the same side, if we, for example, go to this area, which is more, has more influence to plasticity, we have an intersection due to the effects which occur at the notches, that at first, of course, the local plasticity occur, and afterwards, due to the fatigue testing, we have here still some elastic behavior, and so at this level, we get here an intersection, and we have lower influence of the KT for small stress cycles. So the same is, for example, for a steel tested section with the same structure, the same specimen sizes, the same geometry. So here you can see the same results. So we have here for, now I have to go for 10/6 at this side. For example, we have for 10/6, we have around 110 MPa. And for the lowest one, we have sorry, we have a double logarithmic scale, so we have here 200. And at this point, we are around 110 MPa. So also for the steel, you can see the same effect, but also at the same time, you have, for example, the magenta colored line, which is at this part the lowest one, which you can already see here. We have here some specimen which at the same side decrease the linear regression. So due to this, that this point is still in the regression curve, it is always lowering and has an influence. So this is at the end also a point we would skip for the linear, for the regression analysis, because this is just a specimen or a testing which result in a failure. So, okay. So as you can see here, the notches or also the KT has some influence on our fatigue testing. And for example, if we now go into our SN curves, so this is what we have there. The SN curves are showing just a rectangular plate section or some steel bars or some hollow sections. So at the same time, we do not know anything about how it acts, how the opening acts in our SN curve. So therefore, we usually go there and just use the increasement of the stresses, and And so, for example, you can go and say, okay, at this side you have, for example, the plate with the hole and the fixed boundary situation. So at this side we have a fixed boundary situation, and these tables usually you also have applied a Poisson ratio of 0.3, and due to this, with the geometry, you can calculate in the linear elastic calculations some drawings like this. So this is at the end. You just have to know, okay, what is the distance to the edges, what is the size of the hole, and due to this, you can calculate the ratio of rho to d. In this approach, I have chosen a hole with a diameter of 4 and a plate with plate distance to the edges of 20 millimeters. So I get here a value of 0.2. I can go there into my my diagram, and at the end, with the information of the diagram, I get here an KT of 2.3. So this is the same as you would get for a numerical analysis, but still, due to prior times where we didn't have such tools, there is a high amount of tables where you just can go there and find solutions like this. And so what do we have to do now is just to increase our stress range by the factor of 2.3, and this is as it is called in the guidelines, the modified nominal stress concept. So in this case, you just go there and you say, okay, you already have the information of unnotched specimen, and you just increase the part, you just increase the stress ranges. So at the end, this approach is going for an area which is from this time to this time, due to this that at the area of the high cycle fatigue, or of the low cycle fatigue, from 10/3 to 10/5, you have a less influence due to the loading at the site. So at the end, we calculated here an KT of 2.3. So we can go there. Of course, 100 times 2.3 at the end would be 230, and so this would be our detail, our stress range we have to take into account at this level. Okay, so this is, I would say, the main basic tools for the nominal stress concept. Usually you can apply, and you have for the design. So what I now want to switch on is the structural stress concept. So the structural stress concept is still already belongs to the local approaches, and this is sorted here. So at this side, as you can see here, this is always the nominal concept, as we already spoke yesterday and today, and the local approach belongs at this side to the structural stress concept, and this side belongs to the local approach, also like the notch concept and the fracture mechanics. So just to get some basic Sorry. It is somewhat disconnected.